In this video, we have two integrals to evaluate. We'll look at the first one here, and I always like to look to see if the derivative of a denominator or an exponent or something under a radical will give me something in the numerator. So in this case, if I let u equal to the expression in the denominator and then compute du, differential here, the derivative of sine is cosine. The derivative of cosine is minus sine. So that would get, because I have a negative there, that would make this a plus sine of x. So you look at this. This is the same thing that I have in the numerator. Got sine of x, cosine of x, cosine of x. So I can easily transform this into an integral involving the variable u instead of x. So in the numerator, got sine x, cosine x, dx. So this expression in the numerator can be replaced by du. And of course, the expression in the denominator, that's u. So the integral of du over u is the natural log of absolute u. But absolute u, or I should say u, is just right here. So I just replace the u by sine of x minus cosine of x. So natural log of absolute value of sine of x minus cosine of x plus the constant of integration. And there's your answer there for that one. Now for the next one, let's start over here. I'm also going to use a U-substitution for this one. I don't have to. Actually, I'm going to do this one two ways. So let's do it this way. I'll let u equal to x squared plus 5. Notice here the derivative of this expression here in the parentheses is 2x, which is why I have it right there. So for this one, then du is equal to 2x dx. So let's make the transformation here. For x squared plus 5, that's going to be the u. And the 2x times dx right here, that's du. Integrate here with respect to u is just going to be u squared over 2 plus the constant of integration. And then we just make the substitution. The u is replaced by x squared plus 5. Quantity squared over 2. And that's the result. Now let's do this also here. Let's just multiply this out, see what happens on this. So multiplying by 2x here, we get 2x to the third plus 10x. Now we integrate here with respect to x. So adding 1 to this 3 here gives me x to the fourth. And then dividing by 4, that'll be 2 over 4. So this will be 1/2, or I'll put the 2 here. Plus, and then again for the 10x, adding 1 to the exponent there, I get x squared. And dividing by 2 here, 10 divided by 2 gives me 5. And then I get the constant of integration. So I get x to the fourth over 2 plus 5x squared plus c. So if I do it this way, I get this answer. If I do it this way, I get, using the U substitution, I get this answer over here. Now let's see if they're the same. Let's go ahead and square this out here. So I squared that out. X squared squared is x to the fourth. And it's plus. And then we double this product here. Give me 10 x squared plus 25. and that's all over 2. Now they're both answers. So let's check this out. X to the 4th, dividing here by 2, x to the 4th over 2 gives me that term there, no problem. 10x squared over 2, 2 into 10 gives me 5. I get this term right here. But then I get a 25 over 2 left over. So this answer over here is the same thing as this one over here, except I have an extra constant. But that's okay. That's why we have this constant C over here. This can absorb any other constant that we have. So I could just say this 25 over 2 is absorbed into this constant right there. So it's expected when you're solving an integral like this, evaluated integral, and you might have several methods to use. In some cases you can have as many as 2 or 3 methods to work that same integral. And in some cases you're going to get basically the same integral. It's going to differ by a constant. And that's why we have this constant of integration. So they're both acceptable answers here. Thanks for watching. We'll see you next time.